Hello, I'll present our work, DSERT-RoLL, Robust Multimodal Perception for Diverse Driving Conditions with Stereo Event-RGB, Thermal Cameras, 4D Radar, and Dual-LiDAR. This is joint work with Hoonhee Cho, Jaeyoung Kang, and Yuhwan Jung from the Visual Intelligence Lab at KAIST. Let me begin with the motivation. Autonomous driving relies heavily on perception, with conventional RGB and LiDAR setups degrade severely in adverse conditions such as heavy rain, fog, snow, or low light. Novel sensors, event cameras and thermal cameras, 4D radar can complement RGB and LiDAR in these scenarios. However, each novel modality typically exists in its own standalone dataset. As a result, fairly comparing these sensors or fusing them from 3D perception is currently very difficult. This is the gap our work aims to close. To address this, we built a single data collection platform that captures all of these modalities simultaneously. Our vehicle is equipped with stereo event cameras, stereo RGB, thermal, 4D radar, and dual LiDAR, all hardware synchronized and jointly calibrated. To the best of our knowledge, this is the most comprehensive sensor suite assembled for a public driving dataset. Using this platform, we collected data across diverse illumination and weather conditions, including normal, low light, overexposed and HDR scenes, as well as clear, light, and heavy rain, light and heavy snow, and fog. Every frame is annotated with 3D bounding boxes for these object classes: vehicle, pedestrian, and cyclist, providing the labels needed for full 3D perception tests. These are exactly the scenarios where conventional perception fails, making the dataset a stress test for robustness rather than an average case benchmark. Here are paired samples from our dataset, captured at the same time by all 5 modalities under clear, fog, and light snow conditions. This shows the kind of multimodal, multi-condition coverage of our dataset provides. This slide shows samples under even more challenging conditions: heavy snow, light and heavy rain. Under these conditions, no single modality remains fully reliable. Each has its own failure mode, and together they complement one another. Now let me move to our method. Our framework fuses these heterogeneous modalities for 3D object detection. LiDAR and 4D radar are first voxelized into BEV features and combined into a fused BEV representation, which produces initial 3D bounding box proposals. Each camera modality, event RGB and thermal, goes through its own backbone and is then aligned with the 3D voxel space through a camera 3D range sensor fusion module that uses learnable offsets and cross-attention. The features are merged via confidence-based voxel fusion, and a box refinement module produces the final prediction. The design is fully modular. Any modality can be added or removed. The ablation table at the bottom shows that as we add more modalities, performance improves across nearly every condition. Our full setup with all modalities achieves the best overall robustness. Here, we compare our method against baselines grouped by sensor configuration. Single modality baselines all show clear weakness, either failing under adverse weather or limited in fine-grained perception. Our full model achieves the best performance across nearly all conditions, with the largest gains where conventional perception fails. Finally, here are qualitative results against representative baselines. RTNH using 4D radar, VoxelNest using LiDAR, and LogoNet which uses LiDAR and RGB across normal, fog, rain, and snow conditions. Baseline methods often miss objects or produce inaccurate bounding boxes under adverse weather. In contrast, our model produces consistent and accurate 3D perceptions even when individual sensors degrade. To summarize, DSERT-RoLL is the first unified, fully annotated multi-modal driving dataset combining Event-RGB-Thermal, 4D radar, and Dual-LiDAR together with a strong fusion baseline. We hope it will serve as a foundation for future research on robust autonomous perception. Thank you for watching.